All right, well, then I'm going to start. Oh, wait, no, I'm not. All right, there we go. Looking good. So I can see you guys. Oh, dang, everybody got their mic on. I didn't even, camera on. I didn't even see that. Sweet. That's what we're talking about. All right, so we're still talking about basically the hierarchy of reactivity and all that stuff. Um, so, yeah, certain things will be better leaving groups than others. Certain things will be better nucleophiles than others. If you have a good nucleophile and a good leaving group, it's going to go really fast. If you have a bad leaving group and a bad nucleophile, it's not going to happen at all. And basically, there's everything in between. Hopefully, you guys have put that together by now. So, starting out here, we've got amide bonds. If you take biochemistry, you'll hear all you ever could want to hear about amide bonds. So basically, they're pretty stout. A lot of times they need like an acid catalyst to make them make reactions go fast with them and actually like favorable. For this one, while you do have a good nucleophile, like I said, you've got that amide bond, which is not a very good leaving group, and so it's not going to happen. For the second one, you've got an acid halide, which is a great leaving group. Specifically, this chloride is what makes that such a good like leaving group place. I don't know what the word was that I was trying to use there, but yeah, well, probably electrophile. Um, and basically, you can remember these ammonium or amine. Um, I'm not on my phone, so I'm not distracted. These amine nucleophiles as being like kind of mild. They're technically better than oxygen because oxygen wants to hold its electrons pretty closely. But they still have a lone pair, and anytime you've got a lone pair, you could technically have a nucleophile. Um, so yeah, that will happen. The second one is once again got an amide bond, and then a pretty weak nucleophile, so that's not going to happen. And then the last one, you've got a great leaving group. So yeah, these esters make for very stable leaving groups, and then you've got a mild um, nucleophile, so that'll happen. And that's all for that one. Next, we're just talking about basically how you can do nucleophilic addition and how that can be different from like up here where we reformed the carbonyl group in the form of like substitution. When we're doing addition, all that happens is nucleophile attacks, and then it makes an alcohol, and the nucleophile just kind of stays in there. And usually that happens because you've got an acid that can quench uh, that right there, that like epoxide group. So this is kind of the fun stuff that I wanted to talk about. So I always remember this section because for several reasons. Um, one of them is I can play this song. And basically, what you can remember from that is Grignards, organolithium, and hydride ions all hit twice as hard. Twice. Okay, that was bad. And yeah, so they'll reform the carbonyl group, and then once that carbonyl group has been reformed, you can hit it again, and so that's that. Um, Grignard, organolithium, hydride. Those are also all so reactive that usually you don't even have like water. They're usually in ether, and so yeah, remember that. Any questions there? I'm not going to pause for too long because that'll just turn into an awkward silence like it always does. Um, Moving on, now we're talking about how good of a nucleophile these guys are. So this first one, we've got basically an ester. Ester has a pretty good, that ether is a pretty good leaving group. Not as good as if it was an ester, but still a good leaving group. And then that's a mild nucleophile, so that's good enough to happen. For this time, you see organo lithium, or not organo lithium, Grignard, and I want you to hear that twice as hard. And yeah, that's that. So you see this. Uh, you'll notice there's one attack, there's a second attack. That's all there is to it. Next, we've just got reverse esterification. Oh yeah, and these are very strong nucleophiles. Hopefully that was already said a couple times. This is reverse esterification because you got the ester and then now you're just adding acid and water. That's pretty favorable. Those exist on a equilibrium and you can push them one side or the other with Chantelier's principles. For this fifth one, you've got this acid halide, which is a great leaving group. And basically the pyridine is there because when this chloride leaves, it can make hydrochloric acid. Somebody said a couple things in the chat. The singing made my day. Thank you. I'm glad. I know it's bad, and I know my voice cracked probably. But yeah, anyway, moving on. Last one. Twice as hard. So once again, the fun thing that I always remember this unit for is Dr. Nichols like drawing swastikas all over the board, and that's horrible and awful. But like that's how this always ends: is her drawing ethals, and yeah. Anyway, so that's another way to remember that when they're strong, they do twice. When it hits this thing, if you get the reformation of that puppy, it'll do it again. Let me read the chat. Thank you. Okay, moving on. And then remember, you need the acid workup at the very end. Last section here, you've got two equivalents of amide to make you think that you're going to do it twice as hard, but you don't. You do it once because once is for neutralizing the acid halide. That's what 1 mole's for. The other mole is just to act as a nucleophile. So yeah, that's all there is for that one. As far as challenge problems, these are the challenge problems. These look easy. They're not. I mean, I think one group got the challenge problem right. Not chemistry. Anyway. I'm gonna not say anything about one. That's bad. Yeah. Is there any questions about this?
So on F for
all right. So Sharik had a quick question about, basically why you had two equivalents here, and it's not entirely necessary. She was more or less testing to make sure that you knew that this was not a strong nucleophile. But since he did ask, I'll go ahead and explain. Basically, it just meddles with the Chantelier's principles, and so these reactions usually occur in an equilibrium. And so basically, or most of these reactions do. You'll see, first of all, this, here we go, lead down here to, this is the tetrahedral intermediate, where you've got the amine mixing with the epoxide with the chloride. And so basically all of these will lead to the epoxide coming back and making, reforming the ketone. And then also the chloride ion will then leave as a leaving group. And so once that chloride ion has left as a leaving group, it is forming an acid. So that will form hydrochloric acid. So that leaves you with the product here, and then also the this, which will come back and, oops.
Hey Caleb, can you add me back to group 4?
Yes. So, yeah, basically, this right here, this chloride ion, will come back and make this neutral, this amide. So it'll take away one hydrogen, and when it takes away that hydrogen, it forms hydrochloric acid, and then you've got the second mole here to basically just act as a buffer. And so by adding product on this side of the reaction, it will keep it, yeah, it just basically stimulates, gives that proton a place to go that doesn't involve messing up the main product. So yeah, it will basically push the product towards favoring this in the solution. But even if there wasn't that second mole, it wouldn't be necessary. I mean, like, it would still form the same product. But yeah, there's a little bit of, I don't know, MCAT review equilibrium stuff. Oh wait. So now we're doing so coming back to this, basically these just cover a lot of acetoacetic ester synthesis. There's no Grignard, nothing funky going on here. Basically, this is just focusing on really nailing down those essentials, making sure you guys are able to catch a lot of those nifty little tricks that they might sneak in on the ACS. So this first one, pretty much everybody's pretty comfortable with recognizing acetoacetic ester and malonic ester. The only difference is just this little carbon right there, or that molecule rather. Sometimes it's an alcohol group or hydroxyl group. Other times it's a carbon. And when it's a carbon, acetoacetic ester. When it's an alcohol, it's malonic ester. And so, yeah. So this first one is just a matter of connecting the dots. All of these are going to have you remember to use your ethyl oxide and not hydroxyl or just OH because that will saponify your ester, and that's no bueno. So yeah, we'll do that. Basically, just match up these two. Doesn't really matter the order. And then we got to use heat and decarboxylate. So yeah, this acid is to cap off. Well, no, we don't even need the acid. Well, no, we do. Do we? I included the acid because usually you need to fix the energy well here because you know you've got that negative charge here, and basically by putting the acid on it, it caps it. Next, we've got malonic ester. So this one is very similar. The only difference is carboxylic acid. You're adding 1 or 2 chains, and then you'll use heat to decarboxylate off one side. And yeah, that's all there is to that one. The next one is where we start getting into things that can't work. And so you'll notice here, you've got 3 substituents. If you'll remember back in our malonic ester and all those kind of things, there's only 2 hydrogens here. So we can't add a third. If you could add a third, that would be 5 bonds. So only adds twice. Remember that. And so yeah, it's 5 bonds. I went ahead and drew that little nice artsy thing there. So next, this is the 4th one, D. It's pretty simple. Once again, we're just using ethyl oxide, and then we're adding this bad boy. Nothing fun, funky going on here. Once again, this one, it's actually very important you do your acid workup because you don't have the second acidic hydrogen being pulled. And you want to make sure that acidic hydrogen's there, and yeah, make sure it doesn't add twice, it only adds once. And then the heat, that's what this triangle stands for, will just decarboxylate off this ester. So yeah, the next one is not going to work. And so this is the one that a lot of people got tripped up on. Remember to recognize and look for allylic versus vinyl carbons. Those are something that's very important once you get to this part of the semester because they're very different things. A vinyl carbon is planar, and so it basically means that that carbon has sp2, and if you'll remember, sp2 means that there's 3 substituent, it's trigonal planar, and you're trying to remove and take off one of those substituents that keeps it trigonal planar. Well, there's a lot of energy associated with those bonds. You're much more likely to form a tetrahedral and then fall back to basically reform the planar molecule, but almost never, or pretty much never, are you ever going to be able to remove a substituent from that position. And so that's why specifically when we get into Friedel-Crafts chemistry and we get into Diels-Alder, no, not really so much with Diels-Alder, you'll see this carbon has to attack. We don't see as much stuff where, or we don't ever see stuff where somehow or another we're removing this proton. So something is coming in and, well, actually that's probably more likely. this. Never seeing that, because that implies that somehow these electrons are just falling away. And so basically what this reaction would have required would be this molecule right here to work as one of the little substituents for the acidic hydrogen spot. But we can't do that because we can't substitute off, we can't have a nucleophile punch in right here. And that's what SM2 is. So yeah, remember that basically another good way to remember that would be just thinking about it as a conjugation system, so the pi system. You're breaking that pi system when you try and hinder one of these carbons. So when you try and get into, here, let me get a better color, into these carbons, you're breaking a pi system, and that takes a lot of energy, and that's not favorable. But if you want to do, remember, one carbon out, that's allylic. And so that carbon is getting, I think of it as like it's receiving aid from this pi system as far as stability. So this pi system is so stable that a little bit of that stability carries over one carbon over. And that's where you get allylic carbons, and that's A. But if you move one in, then that's just too close, because then you're trying to break the whole pi system, and that's not favorable. So to make this molecule, what I was showing when I talked about this in class was that you would need to use something on the allylic carbon. You would need to start, it's very easy with these types of stuff to start once you've already broken away from the benzene ring, because specifically doing chemistry with benzene rings is difficult because they are so stable. That's something that, like, we talk about in the environment, benzene rings being released into the atmosphere and stuff like that, or into the, I don't know, environment. It's bad because they can't break down, and it will fall into like biochemical reactions, and basically screw them up, because it looks like it's something that the organism will like recognize, but in like actuality, or in reality, that benzene ring is not going to function as like a normal, whatever that substrate for the enzyme was looking for would. So yeah, all that to say, straight benzene rings problematic. It wouldn't work. As far as D, let's see. So we've got malonic esters, and so for this one, basically you're going to once again be working on a phenyl group, but this time what you've got is VRs on the allylic carbon. And so what that means is that, it's very stable. And then after that, we've got just another, what is that? 1, 2, 3, 4, 5, propyl, butyl, pentyl. I don't think that's right. Maybe that's right. Anyway, we've got these two, and this is similar to everything else that we've been doing. It's just a matter of yoink off these acidic hydrogens and plug in these substituents. And then after that, we're going to decarboxylate off that guy right there. So that's all for that one. Next on G, so this is where we get into acetoacetic ester. This one was confusing because people have a lot of trouble recognizing that you can add something like a string of things here, and then have another BR that can swing back. And so this electron group can come back and form a ring like that. I know that looks kind of ugly, but like that will work, and that happens. So for here, I went ahead and color coordinated every carbon, so that you went ahead and you saw like how from the reagent, we get from the reagent to the product. And this looks kind of funky. Really, it would look more like, let's see, 1, 2, 3, 4, 4, like that. That's what that reagent would really look like. And if they threw that at you, then I'm pretty sure the majority of the class would not be able to recognize that as the reagent that makes this ring. But hopefully, as you go through all this Friedel-Crafts and Diels-Alder and Claisen stuff, you start to get more comfortable with seeing these linear, or not technically linear, these alkane strings and flipping them into, or cyclizing them into rings. So the very last part here is H. I think that's the last one. Yeah. Okay, so this one wouldn't work because, once again, it's very important you guys remember that this stuff is adding in an SN2 fashion. And so what's a big thing that blocks SN2 reactions? Steric hindrance. So yeah, basically, we've got malonic ester here. Oops. Here, I'll draw malonic ester real quick. This guy right here is operating to punch in on what would be a cubital group with BR on it. But that is very unstable. Or rather, just wouldn't happen because this massive molecule is not going to be able to fit the other big molecule in a way that they click. Okay, that did not make much sense. I think I clouded the concept of steric hindrance, but hopefully you guys understand that because that's very Orgo 1 concept. It's a fundamentals. But this one would work. You could add that ring. And then once again, you're just going to add heat, and that's how you take away that last bit. I definitely have rambled a lot in this last little bit, but hopefully this was helpful. Like and subscribe. Don't actually. If you guys have any questions, my email is somewhere linked to like Canvas. Yeah. Also, just check my announcements if you're in my recitation. I've given out my email address there a couple times too. You can always email me with questions. Always available. Also, we've always got office hours. Incoming call, spam, and office hours is from now, like 1:30 to 2:30 on Fridays, and then also 8:30 to 10 on Wednesdays. So anyway, all right, y'all have a great week.